So here's something worth thinking about as you settle in tonight. Every atom of calcium in your bones, every single one, was forged inside a star that died before our sun existed. The iron in your blood was made in the collapsing core of a massive star in the final seconds before it exploded. The oxygen filling your lungs right now, the carbon in every cell of your body, the nitrogen woven through your DNA, none of it was here when the universe began. None of it. The universe started almost entirely empty of these things, and all of it, all the raw material of you, was built inside stars. Stars that lived and burned for millions or billions of years, fusing lighter elements into heavier ones in their cores, and then died and scattered everything they'd made across light years of space, where it drifted and cooled and clumped, and eventually, after an almost incomprehensible amount of time, found its way into a molecular cloud, and then into a new star, and then into the debris of a young solar system, and then into a rocky planet, and then into the ocean, and then into a living cell, and then, eventually, into you. You don't notice any of this. Nobody does. The calcium in your skeleton carries no memory of the stellar core that forged it. The iron in your blood doesn't know it was scattered by an explosion. And yet here it is. Here you are, breathing, thinking, made of star stuff so thoroughly and so completely that it is not a metaphor or a poetic flourish. It is a literal, verifiable chemical fact. You are the universe, organized into a shape that can ask questions about itself. And for most of human history, nobody had any idea that any of this was true. Stars were lights, beautiful, fixed, eternal, or so it seemed. Ancient people gave them names and built stories around them and navigated by them. But the idea that stars were born, that they had beginnings and childhoods and eventually died, that they were the universe's factories for building the elements, that the atoms in your body passed through a stellar interior before they became part of you, this was not obvious. It had to be figured out, slowly and painfully, by a long line of scientists working at the edges of what was known, often in the dark, often wrong before they were right, often baffled before they were illuminated. And that's what we're going to talk about tonight, how stars are born. Literally everything about it. The whole long, strange, violent, beautiful process. From the cold, dark clouds of gas drifting between the stars, to the moment a new sun ignites and begins to shine, to what that process means for the existence of everything you can see and touch and breathe. We're going to take it slow, start from the very beginning, and just walk through it together. No rush. If you drift off somewhere along the way, that's perfectly fine. The ideas will still be here, and honestly, some of this makes more sense when you're half asleep anyway, when your mind is loose and open and not trying too hard to force everything into a shape it recognizes. Because that's kind of the first lesson of stellar birth. The universe makes stars in ways that have almost nothing in common with how we might imagine something being born. And the beautiful thing is, you don't need to be an astronomer to follow this. You really don't. Because star formation at its heart is about things you already have intuitions about. Gravity, cold, heat, pressure, the way spinning things tend to flatten out, the way things clump together when you're not watching, the way a spark can light a fire that then sustains itself. The astrophysics can get complicated, sure, but the ideas, the actual core ideas, are surprisingly graspable if someone walks you through them slowly enough. And that's exactly what we're going to do. We're going to take our time. We're going to start well before any star ignites, actually, because the story of how stars are born doesn't begin with a star at all. It begins in the cold dark between stars, in a vast, thin sea of gas and dust that fills the galaxy. that most people never think about, that is, in many ways, the most important material in the universe. And it begins not with a bang, but with something much quieter than that, with cold, with dark, with patience. Let's start where the story actually starts, which is not in a laboratory or on a page of equations, but out in space itself, in the enormous regions between the stars. And to really understand this, we need to let go of something that most of us carry around without realizing it, the idea that space is empty. It isn't, not even close. The space between star systems, what astronomers call the interstellar medium, is filled with stuff. Thin stuff, yes, almost unimaginably thin by any standard we can relate to on Earth, but stuff nonetheless. Gas and dust, permeating every corner of the galaxy, threading through the enormous volumes between star systems like a kind of invisible fog that we've only recently learned to see. Now, for a long time, astronomers assumed that interstellar space was essentially a vacuum. In the early 20th century, the prevailing view was that the space between stars was mostly empty, occasionally interrupted by bright emission nebulae, the colorful clouds of glowing gas you see in photographs, but essentially void. This view began to change in the 1930s, and it changed for an interesting reason. The light from distant stars didn't quite look right. Here's what happened. When astronomers took careful spectroscopic measurements of the light from stars, spreading starlight into a spectrum the way a prism spreads white light into a rainbow, they found narrow absorption lines that didn't belong to the star itself. Lines that stayed fixed even as the star's own spectral lines shifted due to its motion. These stationary lines were being imprinted on the starlight, not by the star, but by material the light was passing through on its way to Earth. Material between us and the star, the first hints of what was actually out there in the dark. The physicist who made one of the key early observations was a German-American astronomer named Otto Struve, working in the 1920s at the Yerkes Observatory in Wisconsin, using its enormous refracting telescope to study the spectra of binary star systems. Struve found calcium and sodium absorption features in starlight that he correctly identified as interstellar in origin, not in the star, but in the space between. This was the beginning of the observational study of the interstellar medium, and like many beginnings in science, it was modest, a strange line in a spectrum, a puzzling measurement. A man at a telescope in Wisconsin, late at night, wondering why the starlight looked wrong. What we know now, after nearly a century of increasingly sophisticated observation, is that the interstellar medium is a complex, dynamic, multi-phase structure. It is not one thing. It is several things, coexisting side by side, sometimes interpenetrating, at vastly different temperatures and densities. There are regions of hot, ionized gas, heated to millions of degrees by the shock waves from stellar explosions, where individual atoms move fast, and collisions are energetic, and the gas glows faintly in X-rays. There are regions of warm, diffuse hydrogen, at temperatures of a few thousand to 10,000 Kelvin, that glow in visible light and in radio waves when the hydrogen radiates. There are regions of cold, neutral hydrogen, the HI, as astronomers call it, using the notation for neutral hydrogen, sitting at perhaps 50 to 100 Kelvin, detectable by the famous 21-centimeter radio emission line. And then, in the coldest and densest corners, there are the molecular clouds, temperatures of 10 to 30 Kelvin, densities hundreds or thousands of times higher than the surrounding medium, the gas so cold that atoms have linked up into molecules, and the whole region is dark and silent and waiting. These different phases are not fully separate. They bleed into each other at their boundaries. They're stirred together by turbulence and magnetic fields and the energy inputs from stellar winds and supernova explosions. The interstellar medium is not a still pond. It's more like a slowly churning sea, with currents and eddies and regions of different temperature rising and sinking, all on timescales of millions of years. Violent on the inside, serene on the outside, if you're watching from a distance. And threaded through all of it are magnetic fields, weak by any terrestrial standard, a few microgauss, roughly 100,000 times weaker than the magnetic field that makes your compass needle point north. But the interstellar medium is so vast, and magnetic fields can act over such enormous distances that these weak fields have real consequences. They guide the motion of charged particles, cosmic rays, ionized gas, along their field lines. They resist compression. They can help support a cloud of gas against gravitational collapse, acting like invisible springs woven through the material. And they can be amplified by the rotation of the galaxy and by the chaotic motions in star-forming regions. Magnetic fields are, it turns out, one of the key players in the story of star formation, a character we'll return to several times. What about the dust? The interstellar medium contains about 1% of its mass in the form of tiny solid particles, grains of silicate and carbon, coated in ice mantles, typically less than a micrometer in size. This doesn't sound like much, but over galactic distances, it adds up. The dust absorbs and scatters starlight, reddening it in the same way that Earth's atmosphere reddens the setting sun. It dims distant objects. It makes whole regions of the galaxy opaque to visible light. For much of the history of astronomy, the dust was an obstacle. It hid things from view. But the dust also does something crucial. It provides surfaces, tiny solid surfaces, floating in the cold gas, where atoms can land and bond to each other in ways they never could in the gas phase alone. The surfaces of interstellar dust grains are where most interstellar molecules form: hydrogen molecules, water, carbon monoxide, more complex compounds. The grains are the catalysts of interstellar chemistry. Without them, the molecular clouds that give birth to stars could not exist. This is the interstellar medium, then, a thin, dynamic, magnetically threaded sea of gas and dust, filling the galaxy, connecting everything to everything else across enormous distances. Most of it will never become a star. Most of it will drift and swirl for billions of years without anything dramatic happening. But in certain places, under certain conditions, it concentrates, it cools, it darkens, and eventually, in the coldest and densest pockets, it begins to do something that will change everything. It begins to fall together. And here is something that sets this apart from almost any other large-scale physical process you might think about. The interstellar medium has memory, not in any conscious sense, but the material drifting through it carries a record of the stars that made it, in its isotope ratios, in the particular mix of elements, in tiny crystalline grains that preserve, in their atomic structure, the temperature and pressure of the stellar environments where they formed. Astronomers can examine primitive meteorites, rocky remnants from the earliest solar system that have survived essentially unchanged, and find within them individual grains of material that predate the solar system itself, grains of silicon carbide that formed in the winds of ancient carbon stars, tiny diamonds assembled in interstellar space billions of years before the sun existed, presolar grains, as they're called, windows into stars that died before our sun was born. The dust drifting between the stars is not anonymous. It is, in some sense, the autobiography of everything that made it, written in crystal and isotope, waiting to be read. And we are beginning to read it. The field of isotope geochemistry, the study of isotope ratios in meteorites and other ancient materials, has opened a window onto the history of the galaxy that no telescope could provide. By measuring the abundances of short-lived radioactive isotopes and their decay products in the oldest solar system materials, scientists can place the formation of the solar system in a timeline of stellar evolution. They can identify the types of stars that contributed material to the pre-solar molecular cloud. They can estimate how long that material drifted in the interstellar medium before being incorporated into the solar system. The stones we find on the ground, or in Antarctica, where dark meteorites stand out against the white ice, are not just rocks. They are messengers from a past so deep it defeats intuition. Now, the places where that falling together happens, the specific structures within the interstellar medium where stars are made, are called molecular clouds. And they deserve a long look, because they are strange and wonderful objects that most people have never heard of, and yet they are responsible for the existence of every star in the sky. Molecular clouds are the largest discrete structures in the galaxy that are made of gas rather than stars. The biggest ones, what astronomers call giant molecular clouds, can be hundreds of light years across. They contain material equivalent to hundreds of thousands or even millions of times the mass of the Sun. The Orion Molecular Cloud Complex, which lurks behind the Orion Nebula and extends across much of the constellation Orion, contains something like 100,000 solar masses of material and spans perhaps 300 light-years. Our galaxy, the Milky Way, contains a few thousand giant molecular clouds arranged mostly in a ring at a certain distance from the galactic center, following the spiral arms. These clouds collectively contain a significant fraction of the interstellar medium's total mass. Why molecular? Because inside these clouds, the gas is dense enough and dark enough that atoms can link up into molecules. In the warmer, more diffuse parts of the interstellar medium, ultraviolet radiation from hot stars prevents molecules from forming. The photons are energetic enough to break chemical bonds almost as fast as they form. But inside a molecular cloud, the outer layers of gas and dust act as a shield. Dust grains absorb the incoming ultraviolet radiation before it can penetrate deep into the cloud. In the interior, shielded from starlight, the gas cools to extraordinary temperatures, 10, 15, maybe 30 Kelvin, and atoms have time to find each other and bond. The most common molecule in molecular clouds is molecular hydrogen, H2, two hydrogen atoms bonded together. It's the dominant constituent by mass. But astronomers can't observe it directly, at the temperatures typical of molecular clouds, because H2 doesn't radiate at radio wavelengths. So astronomers use a proxy molecule, carbon monoxide, CO, which does radiate a characteristic radio signal, and which forms in molecular clouds wherever hydrogen and carbon and oxygen coexist in sufficient abundance. Radio maps of CO emission have been used to map the structure of molecular clouds across the galaxy and through the galaxy beyond. And those maps reveal something important. Molecular clouds are not smooth, uniform blobs. They are hierarchically structured, lumpy and clumped at every scale. Inside a giant molecular cloud, there are clumps, and inside those clumps there are denser regions called dense cores. And inside the densest cores are the sites of individual star formation. The structure is fractal. It looks similar at different scales, with clumping inside clumping inside clumping. This fractal structure is driven by the turbulence that permeates the clouds, constantly stirring the gas, creating regions of higher and lower density. Now, turbulence is something we all encounter in everyday life, in the way smoke curls from a candle, in the way cream swirls into coffee, in the turbulence that rattles an airplane over a mountain range. In all of these cases, a fluid is moving in complex, irregular ways, with energy cascading from large scales to small scales in a hierarchy of eddies and vortices. Something very similar happens in molecular clouds, except on scales of light years and over time scales of millions of years. The clouds are stirred from the outside by the energy of nearby stellar winds and supernova shock waves, and this energy drives turbulent motions that cascade down through the cloud, from large-scale flows to smaller and smaller motions. This turbulence does two apparently contradictory things. On the large scale, it supports the cloud against gravity. The turbulent motions create an effective pressure that resists compression. Without turbulence, a massive molecular cloud would collapse much faster than it actually does. Turbulence slows the collapse and regulates the rate at which the cloud converts its gas into stars. On the small scale, turbulence concentrates the gas. Turbulent flows can create local regions of enhanced density, places where two turbulent streams converge, for example, or where the gas is compressed into a dense filament by the interaction of large-scale flows. These concentrated regions can be pushed over the threshold for gravitational collapse even while the cloud as a whole is still held up. In recent years, with the advent of powerful radio telescopes like the Atacama Large Millimeter Array, ALMA, in Chile, astronomers have been able to map the structure of molecular clouds in extraordinary detail, and one of the most striking things those maps reveal is that molecular clouds are threaded with filaments, long, narrow concentrations of dense gas that look almost like a cosmic web in miniature. Dense cores, the seeds of individual star systems, tend to form along these filaments, strung along them like beads on a string. The filaments themselves seem to form where large-scale flows of gas collide, compressing the material into these narrow structures. And along the filaments, at the densest points, gravity begins to win. The temperature inside a molecular cloud core, a dense core that is about to collapse, is remarkable. 10 Kelvin, maybe 12. That's 10 degrees above absolute zero, the coldest temperature physically possible. To put that in context, the surface of the Sun is about 5,700 Kelvin. The surface of the Earth, on a mild day, is about 290 Kelvin. The interior of a molecular cloud core is about 10. It is one of the coldest environments in the known universe, colder than most of the cosmos, cold enough that the gas barely moves at all, cold enough that the faintest gravity can begin to matter. And that is precisely the point. Here's the thing about gravity. It is the weakest of the four fundamental forces, dramatically weaker than electromagnetism, weaker than the strong nuclear force, weaker than the weak force. A bar magnet can easily pull a steel paperclip off a table, overcoming the gravitational pull of the entire Earth. A child's balloon, given a small static charge by rubbing it on your hair, will stick to a wall against gravity's pull. By any comparison of fundamental forces, gravity is pathetically weak. And yet gravity rules the universe on large scales. It governs the motions of planets and stars, and galaxies and galaxy clusters. It shapes the large-scale structure of the cosmos. How? Because gravity is long-range and one sign. Every other force, electromagnetism, the nuclear forces, tends to cancel out at large distances. Positive and negative charges attract and cancel. The nuclear forces act only at subatomic scales, but gravity has no negative charge. Every bit of mass attracts every other bit of mass, always, with no cancellation over any distance, and that means that given enough mass and given enough time, gravity always wins. In a molecular cloud, the gas is cold enough that the thermal pressure, the outward push of the gas, driven by the random motion of its molecules, is barely enough to hold itself up. The molecules in a 10 Kelvin gas are moving at perhaps a few hundred meters per second, fast by human standards, but compared to what thermal motion would be at room temperature, sluggish. The pressure is low, And in the densest cores of the molecular cloud, where the gas has been concentrated by turbulence or compressed by an external event, gravity begins to pull harder than the pressure can resist. This is captured mathematically in something called the Jeans criterion, worked out by the British physicist James Jeans in 1902. Jeans found that there's a critical mass, now called the Jeans mass, for a cloud of gas at a given temperature and density. If the cloud is less massive than the Jeans mass, thermal pressure wins. The cloud is stable. If the cloud exceeds the Jeans mass, gravity wins. The cloud collapses. James Jeans was born in 1877 in the seaside town of Ormskirk in Lancashire, England. He was one of those early 20th century British scientists who moved easily across mathematics, physics, and astronomy, a natural polymath in an era when the boundaries between fields were more fluid than they are today. He was a Fellow of Trinity College, Cambridge, then a professor at Cambridge, and later a research associate at the Mount Wilson Observatory in California. He was knighted in 1928. He wrote popular science books that were bestsellers in their day. He had a gift for explanation, a sense that the big ideas of physics should be communicable to anyone patient enough to follow them. His work on gravitational instability was, at the time, a piece of mathematical physics aimed at understanding the formation of the solar system, not star formation. He was asking, under what conditions does a rotating disk of gas fragment into clumps? The answer led him to the stability criterion we now call the Jeans mass. And while his solar system models turned out to be wrong in their specifics, the mathematics was right. The Jeans mass, the critical threshold at which gravity overcomes pressure, is one of the fundamental quantities in stellar physics. What the Jeans criterion tells us, in practice, is that cold gas has a lower Jeans mass than warm gas. A pocket of gas at 10 Kelvin can collapse under its own gravity at much lower masses than a pocket of gas at 1,000 Kelvin. This is why molecular clouds are the sites of star formation and not the warmer, more diffuse regions of the interstellar medium. In the warm medium, a region would need to accumulate an enormous amount of mass before gravity could take hold. In the cold interior of a molecular cloud, relatively modest concentrations, containing perhaps a few times the mass of the sun, can cross the threshold. But knowing the threshold isn't the same as knowing what tips a particular cloud core over it. What actually triggers the collapse? This is one of the active research questions in star formation, and the answer is probably several things, depending on the situation. Turbulence, as we've discussed, can concentrate gas into dense regions. Two turbulent streams colliding can push gas into a pocket of enhanced density, and if that pocket exceeds the Jeans mass, it begins to collapse. This is probably the most common trigger in typical molecular clouds. The ongoing turbulence is constantly producing density fluctuations, and some of those fluctuations are dense enough to collapse. Magnetic fields complicate this. Molecular clouds are permeated by magnetic fields, and the field lines resist compression. When you try to push magnetized gas together, the magnetic pressure pushes back. In many molecular cloud cores, the magnetic field is strong enough that it can prevent collapse even if the gas exceeds the Jeans mass. But there's a process called ambipolar diffusion, a slow drift of neutral gas through the charged particles that are tied to the field lines, that can allow the magnetic field to gradually weaken in a dense core over timescales of millions of years until gravity finally wins. Ambipolar diffusion is thought to be important in the quieter, less turbulent molecular clouds, where collapse happens slowly and relatively few stars form. And then there are the external triggers, a shock wave from a nearby supernova sweeping through a molecular cloud, compressing a region of gas and pushing it over the Jeans threshold in a geologically brief moment. or the spiral density waves that sweep through the disk of the galaxy periodically, compressing the interstellar medium as they pass and triggering star formation along their leading edges, which is why the spiral arms of galaxies are studded with young blue stars and glowing emission nebulae, or the collision of two molecular clouds, which can trigger compression at their interface, or simply the radiation and winds from a newly formed star in the same cloud, pushing outward and compressing adjacent gas into collapse, a process sometimes called triggered star formation, in which one generation of stars plants the seeds of the next. Think about that last one. A star forms inside a molecular cloud. As it ignites and shines, it pours radiation and stellar wind into the surrounding gas, carving out a cavity, compressing the surrounding cloud at the edge of that cavity, and that compression may be enough to push nearby cloud cores over the threshold, triggering their collapse, forming new stars. The act of being born can cause others to be born. There's something almost miraculous about that. Whatever the trigger, the result is the same. A dense core inside a molecular cloud, containing a few solar masses of gas at temperatures near absolute zero, beginning to fall inward under its own gravity. Slowly at first, then faster. A star is starting to be made. When the collapse begins, it is almost unimaginably gradual by human standards. A molecular cloud core that has just crossed the gene's threshold might take hundreds of thousands of years to contract significantly. It falls inward at fractions of a kilometer per second. Not fast enough to feel like motion, not dramatic enough to notice on any human timescale. Just a slow, patient, inexorable inward drift of cold gas. But from the beginning, something important is happening. The outer layers of the core are falling faster than you might naively expect. As the core collapses, the center becomes denser and the gravitational pull of the center grows stronger. A stronger gravitational pull draws in the outer material faster, which makes the center denser still, which makes the pull stronger. The collapse is self-amplifying, a positive feedback loop that accelerates as it goes. Early theoretical models of this process showed that the collapse is not uniform. The center collapses first, becoming very dense, while the outer layers are still relatively far out. The core structure looks, at any given moment, like a dense central knot surrounded by a still falling envelope. This inside-out collapse is one of the characteristic signatures of star formation. Now, as the gas falls inward, it compresses, and compression heats gas. This is a fundamental thermodynamic fact, something you experience when you pump up a bicycle tire and feel the pump get warm, or when you use a hand pump to inflate a basketball and notice the valve warming up. Compress a gas and the molecules are crowded closer together. Their random thermal motion is amplified by the compression, and the temperature rises. In the very early stages of the collapse, the core is still transparent enough, still thin enough, that this heat can escape. Photons produced by the warming gas travel outward and carry the heat away into space, keeping the gas temperature close to constant. This is called isothermal collapse. The temperature stays roughly the same, even as the density increases dramatically, and during this phase, the collapse is fast and free. Without a buildup of pressure, there's nothing to slow it down. This isothermal phase lasts until the core reaches a density, roughly 1,000,000,000,000 times greater than the initial molecular cloud. At that density, still far less dense than water, but vastly denser than the interstellar medium, the core becomes opaque to the infrared radiation it's emitting. The photons can't escape anymore. They bounce around inside the increasingly dense gas, trapped, and now the heat of compression accumulates. The temperature begins to climb. When the temperature starts to rise, pressure starts to rise, and pressure pushes back against the collapse. This is the transition from isothermal to adiabatic collapse, the moment when the core stops being transparent and starts trapping its heat. And when this happens, the collapse slows dramatically. The first pressure-supported object forms at the center of the collapsing core. Astronomers call this the first core, or the first Larsen core, after Richard Larsen, the theoretical astrophysicist who first described this stage of collapse mathematically in the 1960s. The first core is not yet a star. It's a warm, dense, opaque blob of gas, supported by thermal pressure, roughly the size of our solar system, with a temperature of perhaps a few hundred Kelvin, not hot enough for fusion, but hot enough to glow, hot enough to be luminous, and still accreting, still surrounded by infalling gas that is streaming down onto it, adding to its mass. This first core phase is brief, maybe a few thousand years. As the outer envelope continues to rain material onto the first core, it heats up further. Eventually, at a temperature of around 2000 Kelvin, something happens. Molecular hydrogen, the dominant gas in the core, begins to dissociate. The H2 molecules break apart back into individual H atoms, and this dissociation absorbs energy from the gas, preventing the temperature from rising as fast as it otherwise would, which means the pressure fails to keep up with gravity. The first core collapses again, a second collapse, on a timescale of years to decades. This second collapse is much faster than the first, because the molecular hydrogen dissociation effectively reduces the pressure support. And at the end of this second collapse, the core has become much smaller and much hotter. Temperatures of thousands of Kelvin at the center, compressed into a region roughly the size of the Sun, or a few times its size. This is the protostar proper, the true beginning of what will eventually become a star. And now it is embedded in a cocoon of infalling gas and dust, being fed from the surrounding molecular cloud, and, if you could somehow see it from a great distance through the dust, glowing brilliantly in infrared light, not yet burning with nuclear fusion, but hot, dense, luminous, and growing. The beginning. Around the central protostar, the infalling gas is doing something remarkable. It is not falling straight in. Almost nothing in the universe falls straight toward the center of a gravitational field, because almost nothing in the universe is perfectly still to begin with. The molecular cloud core from which the protostar is forming had a slight rotation, a slow, barely perceptible spin, driven by the same turbulent motions and tidal forces that pervade the galaxy. That slight rotation, almost negligible at the scale of the cloud, becomes enormously important as the gas falls inward. The reason is conservation of angular momentum. Angular momentum, the product of mass, velocity, and distance from the rotation axis, is conserved in the absence of external torques. If you bring mass closer to the center of rotation while keeping the angular momentum constant, the rotation speed must increase. This is why a figure skater spins faster when she pulls her arms in. It's why water draining from a bathtub spins into a vortex as it approaches the drain, and it's why infalling gas around a protostar doesn't fall straight in. As the outer gas falls inward from distances of perhaps a fraction of a light year to distances of a few times the Earth-Sun distance, it has to spin up enormously to conserve its angular momentum. Gas falling in along the poles, along the rotation axis, doesn't have much angular momentum to begin with, because it's moving nearly parallel to the axis. It can fall in relatively easily. But gas falling in near the equator is trying to fall inward while rotating, and centrifugal effects deflect it sideways. Instead of falling straight to the center, this equatorial gas ends up orbiting the protostar, circling it, settling into a flat, rotating structure, a disk, the accretion disk. This disk is, in many ways, the most consequential structure in the story of star formation. because it is not just a feature of the protostar's early life. It is the birthplace of planets. In the disk, the conditions are right for dust grains to collide and stick, for pebbles to form, for pebbles to accumulate into rocks, for rocks to build into planetesimals, and eventually for planetesimals to sweep up their surroundings and become planets. The disk is where solar systems are made, and it forms naturally, inevitably, as a consequence of the same angular momentum conservation that governs everything from figure skaters to galaxies. A typical protostellar disk is huge by solar system standards. It might extend from very close to the protostar, a few stellar radii, out to 100 or 200 astronomical units from the center. Recall that 1 astronomical unit is the Earth-Sun distance, about 150 million kilometers. So the disk might stretch from near the surface of the protostar out to 2 or 3 times the distance from the Sun to Neptune. That's big. Across this vast expanse, conditions vary enormously. Hot and dense, close to the center, where the gas is heated by radiation from the protostar, cold and icy on the outside, where sunlight barely reaches. The structure of the disk is not smooth, it is turbulent, driven partly by a process called the magnetorotational instability, discovered theoretically in the 1990s, in which the interaction between magnetic fields and the differentially rotating disk gas drives turbulent motions that transport angular momentum outward. Angular momentum transport is crucial. For material to fall from the disk onto the protostar, it has to lose angular momentum somehow, otherwise it would just keep orbiting and never spiral in. The turbulence, driven by the magnetorotational instability, is one of the key mechanisms for this transport. It carries angular momentum from the inner disk outward, allowing inner material to fall inward while the outer disk expands. And then there are the jets. One of the most spectacular discoveries of late 20th century astronomy was that young protostars routinely produce narrow, highly collimated jets of gas, shooting outward from the protostar along its rotation axis at speeds of hundreds of kilometers per second. These jets were first detected in the 1970s and 1980s as radio astronomers began to carefully map regions of active star formation. They found elongated structures of high-velocity gas extending from points associated with young stellar objects, sometimes stretching for light years in both directions from the protostar. Nobody had predicted them clearly. They were a surprise that required a new understanding of how accretion and magnetic fields interact. The picture that has emerged is something like this. As gas flows through the accretion disk toward the protostar, it is threaded with magnetic field lines that are anchored to the disk. As the disk rotates, it winds up these field lines, like a wire wrapped around a cylinder. The wound-up magnetic pressure builds up, and eventually it launches some of the gas along the field lines, out along the rotation axis, at very high speeds. The jets carry away energy and angular momentum from the inner disk and the protostar, which is essential for the accretion to continue. Without some mechanism to shed angular momentum, the protostar would spin up so fast it would become unstable. The jets are the exhaust system, the mechanism by which the spinning, accreting system manages its angular momentum budget. Think about what this means. Here is a young protostar, completely invisible to optical telescopes, buried inside its cocoon of gas and dust. It is actively pulling material in from its surroundings, accreting mass from the disk, and simultaneously, it is firing twin jets of gas out along its poles, shooting that gas into the surrounding molecular cloud at hundreds of kilometers per second. It is both eating and exhaling, constantly and at the same time, ingesting from the equatorial disk, expelling from the poles. The jets punch into the surrounding cloud material, creating hollow cavities, driving shock waves into the gas, stirring up the molecular cloud around the protostar. They are, in a sense, the protostar announcing itself, making its mark on the surrounding environment even before it becomes visible as a star. The jets also do something that makes the story of star formation more complex and more interesting. They interact with the surrounding molecular cloud in ways that can both suppress and trigger further star formation. A protostellar jet punching into a neighboring dense core can compress it, potentially triggering its collapse. The same jet, heating and stirring the surrounding gas, can also disrupt other potential collapse sites, preventing star formation nearby. One young star being born affects the births of others, sometimes helping, sometimes hindering. The molecular cloud is not a passive backdrop, it is a dynamic system in which the stars being born are actively reshaping the environment in which future stars will form. The accretion phase, with its disk and jets and infalling envelope, can last for several 100,000 years for a sun-like star. During this time, the protostar steadily grows in mass, accumulating material from the disk, and gradually, over this time, the surrounding envelope of gas and dust is consumed or blown away by the jets and outflows. The protostar becomes less deeply buried. Eventually, some of the radiation from the central object begins to escape through the thinning envelope, and at some point, the protostar becomes visible for the first time, not through infrared instruments only, but in the wavelengths of light that human eyes can see. It is not yet a star, but it is getting there. The phase that follows, what astronomers call the pre-main sequence phase, or more specifically the T-Tauri phase for sun-like stars, is in many ways the strangest chapter in a star's early life. The T-Tauri phase is the teenage years of a star, tumultuous, energetic, variable, dramatic, and destined to settle eventually into something more calm. The name comes from T-Tauri itself, a star in the constellation Taurus that was discovered in 1852 by the English astronomer John Russell Hind while he was surveying the sky for minor planets. Hind noticed a star near a nebula that hadn't been charted before. The star was variable. Its brightness changed on timescales of days, and it was associated with a patch of glowing nebulosity that seemed connected to it somehow. It was catalogued as T Tauri, the 19th variable star identified in Taurus. The naming convention at the time used letters for variable stars in each constellation. For decades, T Tauri was just one unusual variable star among many. But in the 1940s and 1950s, when astronomers began to systematically study star-forming regions, looking at the populations of stars associated with molecular clouds and dust complexes, they kept finding similar objects, stars that were variable, stars that were surrounded by emission nebulae, stars that showed unusual spectral features, emission lines that indicated they were throwing off material in powerful winds, stars that, when plotted on a diagram of brightness versus color, sat not on the main sequence, the band where stable, hydrogen-burning stars live, but above it, in positions that could only be explained if they were still contracting and had not yet settled into stable hydrogen fusion. George Herbig, an astronomer working at Lick Observatory in California, was instrumental in studying and characterizing these objects in the 1950s and 1960s. The class of objects became known as T Tauri stars, and they turned out to be nothing less than young, pre-main sequence solar-type stars caught in the act of being born. A T Tauri star has, by this point, contracted to roughly the size of the Sun, or a few times larger. Its interior is hot, hundreds of thousands of Kelvin at the center, but not yet at the 10 million Kelvin needed to sustain hydrogen fusion. The star is luminous, shining not from nuclear energy, but from the gravitational energy of its ongoing contraction. This Kelvin-Helmholtz contraction, as it's called, named for the 19th century physicists Lord Kelvin and Hermann von Helmholtz, who correctly identified it as the sun's power source before nuclear physics was understood, heats the star as it slowly shrinks. Over millions of years, the core temperature climbs toward the fusion threshold. On the outside, a T-Tauri star is a storm of activity. It rotates rapidly, sometimes completing a full rotation in just a few days compared to the sun's current 25-day rotation. This rapid rotation drives an intense magnetic dynamo in the star's convective outer layers, generating magnetic fields far more powerful than the sun's current field. These fields produce enormous star spots, dark regions on the stellar surface where intense magnetic fields suppress convection and make the surface cooler, covering 20, 30, sometimes 50% of the stellar surface. As the star rotates and the spots come in and out of view, the star's total brightness fluctuates. This is one of the main causes of T-Tauri variability. But the spots are not the most dramatic manifestation of the magnetic activity. T-Tauri stars flare, enormous magnetic flares, eruptions in which twisted magnetic field lines snap and reconnect, releasing huge amounts of energy very rapidly, sweep across the stellar surface, producing bursts of X-ray and ultraviolet radiation far more intense than anything the modern sun produces. A large flare on a T-Tauri star can briefly increase the star's X-ray luminosity by a factor of 100 or more, bathing the surrounding disk in intense ionizing radiation. These flares may have profound effects on the chemistry and dynamics of the disk, and possibly on the earliest stages of planet formation. And then there are the winds. T-Tauri stars drive powerful stellar winds, streams of charged particles flowing outward from the star at speeds of hundreds of kilometers per second. These winds are far stronger than the modern solar wind, which is itself already an impressive stream of particles. The T-Tauri wind interacts with the inner disk, stripping gas away from the disk's inner edge, gradually clearing the disk from the inside out. It also interacts with the large-scale magnetic field, potentially helping to drive the jets that we saw during the protostellar phase. Over millions of years, the wind erodes the disk, gradually reducing its mass. When the disk gas is finally cleared, when the wind has blown away all the gas that wasn't locked up in solid bodies, the planet formation epoch ends. Whatever planetary system has formed is what you're left with. During the T-Tauri phase, something else is happening. Something small but profoundly consequential. The disk surrounding the star is not just a passive disk of gas. In it, tiny solid particles, dust grains, ice particles, the debris of the interstellar medium, are colliding with each other, and some of those collisions stick. Grains that collide at low velocity tend to stick together rather than bouncing or fragmenting. Over time, small grains accumulate into larger ones. Larger grains collect more material. The growth of solid particles in a protoplanetary disk, from micrometer-sized dust grains to millimeter-sized pebbles, is a slow process, driven by gentle collisions in the gas-rich environment of the disk. As the particles grow larger, to centimeters, then tens of centimeters, then meters, the process becomes more complicated. At these scales, collisions can be destructive rather than constructive, fragmenting the larger bodies rather than growing them. This is one of the major challenges in understanding planet formation. How do you get from meter-sized rocks, which tend to collide and break each other apart, to kilometer-sized planetesimals, where gravity can take over? This is called the meter-scale barrier, and it's an active area of research. Some mechanisms involve particle trapping in eddies in the gas, where particles can concentrate and self-gravity can begin to matter. Others involve rapid streaming instabilities that locally pile up particles in dense clumps that collapse. Whatever the mechanism, planetesimals do form. We know this because we live in a planetary system, and we can observe planetesimals in other systems. But the detailed pathway from dust to planetesimals remains one of the rich open questions in planetary science. These filamentary structures were known to exist from ground-based radio observations, but it was the Herschel Space Observatory, a European Space Agency mission operating in the far infrared, launched in 2009, that first mapped them across entire molecular cloud complexes with the clarity needed to appreciate their universality. Herschel's images of nearby molecular cloud complexes like Aquila, Perseus, and Polaris revealed a cosmos of filaments, an interlocking web of dense gas threading through the clouds, with dense cores appearing preferentially along the most prominent filaments. This was not a coincidence. It appeared to be a fundamental feature of how star-forming regions are organized. The width of these filaments turns out to be remarkably constant across different molecular clouds and across a range of physical conditions, typically about 1/10 of a light year. The fact that this preferred width appears regardless of the larger environment suggests that a specific physical mechanism sets it. The leading candidate involves the balance between thermal pressure of the gas and the pressure of the magnetic field threading the cloud. The field resists compression in certain directions while allowing it in others, channeling gas into thin sheets and filaments. The dense cores themselves, the seeds of individual star systems, are small, a few tenths of a light year across, containing a few times the mass of the Sun. Their internal temperatures, measured from the rotational emission of molecules like ammonia, are remarkably uniform, 7 to 12 Kelvin in the coldest and densest ones. They rotate slowly, completing a full rotation in millions of years, and in the very densest of them, just on the verge of collapse, the molecular emission lines show hints of the inward motions that will eventually build a star, subtle spectral signatures of gas falling toward a center that does not yet exist. There is another T Tauri phenomenon worth understanding, because it changes our picture of how material actually gets from the disk onto the star. For many years, astronomers assumed that material in the inner disk simply spiraled inward and fell onto the protostar in a continuous, uniform flow. The reality, as revealed by careful spectroscopic observations of T Tauri stars over the past few decades, is more interesting and more dramatic. In most T Tauri stars, the inner disk, the region within a few stellar radii of the star, is largely cleared of gas, not completely empty, but substantially depleted compared to the outer disk. This clearing is caused by the star's strong magnetic field, which threads through the inner disk and essentially scoops the gas up off the disk surface, channeling it along magnetic field lines and directing it to fall onto the star not uniformly, but in focused streams, accretion columns, that hit the stellar surface at specific locations near the magnetic poles. These impact points are hot. The infalling gas is heated to tens of thousands of Kelvin as it slams into the stellar surface, creating bright hotspots that rotate with the star and produce the characteristic periodic brightness variations seen in many T Tauri stars. This process, called magnetospheric accretion, has important consequences. The geometry of the accretion columns means that the accreting gas doesn't just slide quietly onto the star, it hits hard, creating shock waves that emit X-ray and ultraviolet radiation. This radiation illuminates the inner disk from above, affecting its chemistry and temperature structure, and the interaction between the stellar magnetic field and the disk creates a torque that can either spin the star up or spin it down, depending on the relative rotation rates of the star and the inner disk. This is thought to be one of the mechanisms that gradually slows the star's rotation over the T-Tauri phase, preparing it for the much gentler rotation rate it will have when it reaches the main sequence. Later in the T-Tauri phase, after a few million years, something else happens in many disks. A gap opens, not at the inner edge, but in the middle of the disk. The surface density of gas drops dramatically in an annular region, producing a ring-like gap. In some systems, multiple gaps form. These gaps are thought to be created by the gravitational influence of forming planets, planets massive enough to push the surrounding disk material outward of their orbit and inward, creating a cleared zone around themselves. The discovery, in recent years, that disk gaps are common, that ALMA images of nearby protoplanetary disks routinely show ringed structures with gaps at various radii, has been one of the most exciting developments in planet formation research. It suggests that planet formation begins remarkably early, perhaps within the first million years of a disk's existence. Young planetary systems may be forming their first planets while the protostar is still in its T-Tauri phase, while the star itself is still variable and flaring and blowing winds. What we do know is that the T-Tauri phase, lasting roughly 1 to 10 million years for a solar-type star, is when the raw material of the planetary system is organized. The dust coalesces into solids. The solids grow into larger bodies. The larger bodies interact gravitationally. The architecture of the planetary system begins to take shape. And all the while, in the center of the disk, the protostar continues its slow contraction, its center heating degree by degree, inching toward the threshold where something remarkable will happen. Now, much of what we know about the early lives of stars comes from objects called Herbig-Haro objects, and they deserve a moment because they are among the most visually stunning and scientifically revealing things we can observe in stellar nurseries. Herbig-Haro objects are bright patches of nebulosity associated with newborn stars. They form where the jets fired by protostars crash into the surrounding gas and dust of the molecular cloud. The jet material, traveling at hundreds of kilometers per second, slams into the slower-moving cloud material and heats it to thousands of Kelvin. The shocked gas glows, emitting light at very specific wavelengths from hydrogen, sulfur, oxygen, and nitrogen atoms excited by the collision. And because jets travel in both directions, one above and one below the protostar's disk, Herbig-Haro objects typically come in pairs, one on each side, sometimes stretched into long chains of glowing knots extending for light years from the central source. They are named for George Herbig and Guillermo Haro, who independently cataloged unusual nebular patches in the Orion star-forming region in the late 1940s and early 1950s. Herbig, working at Lick Observatory, and Haro, working at the Tonantzintla Observatory in Mexico, both noticed that certain bright blobs had spectra unlike any known type of nebula. They were new, puzzling. It took decades to understand that these were jet impacts, the visible footprints of invisible jets being fired by protostars buried in the dust. If you've drifted off somewhere along the way, that's fine. The ideas will still be here when you come back. No need to hold all of this perfectly in mind. Let it wash over you. Some of it will stick, and some of it will drift, and both are okay. What makes Herbig-Haro objects scientifically valuable, beyond their considerable beauty, is that they move, fast enough that over years or decades, astronomers can watch them change. The knots in the jet travel outward from the protostar and can be tracked from one set of images to the next. By measuring how fast the knots move across the sky and combining that with measurements of velocity along our line of sight, astronomers can determine the jet's true three-dimensional motion. And by watching how the morphology of the shocked gas changes over time, as new knots emerge and older ones expand and fade, they can reconstruct the history of the jet's activity. Protostars don't fire their jets steadily. They pulse. Periods of stronger outflow alternate with periods of weaker outflow, each pulse producing a new knot that crashes into the surroundings. These time-varying jets tell us about the time-varying accretion in the disk, the irregular way material falls onto the protostar, sometimes feeding it more and sometimes less. The most dramatic example of episodic accretion is a class of objects called Fu Orionis stars, named for the star Fu Orionis in the constellation Orion, which in 1936 suddenly brightened by a factor of about 100 over the course of a few months and has remained bright ever since. Fu Orionis events appear to be episodes of dramatically enhanced accretion, in which a large amount of material falls from the disk onto the protostar rapidly, releasing an enormous burst of energy. The protostar brightens dramatically, and it may take decades to centuries to return to its previous state. What triggers these events is not fully understood. One possibility involves gravitational instabilities in the disk, sending clumps of material rapidly inward. But they may be common in the early lives of young stars and may play an important role in building up stellar mass. All of this, the jets, the Herbig-Haro objects, the disk structure, the episodic accretion, has been studied for decades with radio, infrared, and visible light telescopes. But in 2022, the James Webb Space Telescope changed everything. Webb is the most powerful space telescope ever built, observing primarily in the infrared, wavelengths that penetrate the dust-obscuring star-forming regions. Its mirror is 6.5 meters across, its sensitivity is extraordinary, and its first science observations included images of star-forming regions that astonished even experienced astronomers. One of the most celebrated early Webb images was of the cosmic cliffs, the edge of a stellar nursery called NGC 3324 in the Carina Nebula. In the image, a dramatic cliff of molecular gas rises above the illuminated surface of the nebula, with dozens of young stellar objects embedded in it, their jets poking through the gas in brilliant columns, previously invisible in optical light. Webb revealed these jets, dozens of them, many oriented in roughly the same direction, suggesting a coherent magnetic field threading the region that organizes the rotation axes of the forming stars. We are, right now, in a golden age of stellar astronomy. Webb in space, the Atacama Large Millimeter Array on the ground, gravitational wave detectors, and the next generation of extremely large optical telescopes being built. These are giving us a view of the universe that previous generations could barely imagine. Questions that seemed intractable a decade ago are yielding to new data, and new questions are emerging that nobody had thought to ask. That is what science does, not just answering questions, but revealing that there are far more of them than anyone realized. The temperature at the center of a contracting pre-main sequence star rises slowly, very slowly. It takes millions of years. The star is contracting at a rate so slow as to be imperceptible on any human timescale, shrinking by a tiny fraction each year, converting the energy of that contraction into heat. But the center is heating, 1 million Kelvin, 2 million, 5 million, 8 million. And before the main fusion process ignites, there is a dress rehearsal. Embedded in the gas of the collapsing molecular cloud, and therefore incorporated into the protostar during its formation, are trace amounts of deuterium, a heavy isotope of hydrogen, in which the nucleus contains 1 proton and 1 neutron instead of just 1 proton. Deuterium is relatively rare. Only about 1 atom in every 40,000 hydrogen atoms is deuterium, but it is chemically identical to ordinary hydrogen, and so ends up inside the forming protostar, along with everything else, and deuterium fuses at a lower temperature than ordinary hydrogen, at temperatures of around 1,000,000 Kelvin, temperatures that a contracting protostar reaches relatively early in its evolution. Deuterium burning can begin. This early fusion of deuterium is not enough to power the star permanently. There simply isn't enough deuterium. The protostar can burn through all its deuterium in perhaps a few 100,000 to a few million years. But while it lasts, deuterium burning has an important effect. It temporarily halts the contraction. The energy released by deuterium fusion is enough to create pressure support, stopping the Kelvin-Helmholtz contraction and holding the star at a relatively constant size and temperature for a while. And when the deuterium runs out, the contraction resumes. But the central temperature keeps climbing. 9,000,000 Kelvin, 9.5, 10. At 10,000,000 Kelvin, a temperature so extreme that it is almost beyond imagination, something becomes possible in the core of the contracting star that is not possible anywhere else in the natural solar system. Protons, hydrogen nuclei, can fuse, not in the sense of simply sticking together at their surfaces, but in the quantum mechanical sense, tunneling through the electromagnetic repulsion barrier between them, getting close enough for the strong nuclear force to take over and bind them. The proton-proton fusion chain begins. And this is the moment, the birth. Not the first collapse, not the formation of the protostar, not even the ignition of deuterium. The birth of a star, the moment it becomes genuinely, permanently a star, is the moment sustained hydrogen fusion ignites in its core. Because fusion is self-sustaining in a way that no previous energy source was. The energy released by fusion creates pressure, which holds up the star, which keeps the core at the temperature needed for more fusion, which releases more energy, which creates more pressure. It is a stable equilibrium, a feedback loop that balances gravity, and it will continue, for this star, for billions of years. The physics of what happens in those first moments of fusion ignition are subtle. The fusion does not begin everywhere in the core at once. It starts at the very center, where the temperature is highest, and gradually expands outward as the energy from those first reactions heats the surrounding gas. As the energy production rate increases, the pressure in the core increases, which causes the star to expand slightly, puffing up a little, pushing its outer layers outward. This expansion cools the core slightly, reducing the fusion rate. The expansion overshoots, then the star contracts back, slightly overshooting the other way. Over thousands of years, the star oscillates toward an equilibrium, a stable size and temperature at which the energy produced by fusion in the core exactly balances the energy radiated from the surface. The protostar settles, the variability calms, the jets die down, the disk continues its slow evolution. The star has arrived on the main sequence. It is, now, a star. Now, let's take a moment with the proton-proton chain itself, because it is genuinely extraordinary. When two protons fuse, they don't simply combine. They undergo a transformation. One of the protons converts into a neutron, releasing a positron, an anti-electron, and a neutrino in the process. This transformation is mediated by the weak nuclear force, which is itself a remarkable thing. The very weakness of the weak force is what makes stars shine as long as they do. If the weak force were stronger, protons would fuse more easily, and stars would burn through their hydrogen far too quickly to allow the billions of years of stable burning that life seems to need. The feebleness of the weak force, counterintuitive as it sounds, is part of what makes the universe habitable. The neutrinos released in the proton-proton chain are extraordinary particles in their own right. They interact with matter so weakly that they can pass through the entire sun, from core to surface, without being absorbed. They stream out of the sun at nearly the speed of light and travel across space essentially unimpeded. Right now, as you settle in for sleep, approximately 65 billion neutrinos from the sun are passing through every square centimeter of your body every second. Through your pillow, through the floor, through the earth. 65 billion per square centimeter per second, passing through you as if you weren't there. You cannot feel them. Nothing can stop them. Just sit with that for a second. The energy released by each proton-proton chain reaction, 4 protons combining to make one helium nucleus, is tiny, about 4 times 10 to the minus 12 joules. But in the sun's core, this reaction happens roughly 9 times 10 to the 37th times per second. That's 9 followed by 37 zeros per second. And collectively, all those tiny reactions add up to 4 times 10 to the 26th watts of power, the luminosity of the sun, enough to sustain life on Earth, enough to drive the weather, enough to power every photosynthetic organism that has ever lived on this planet. All of it from the tunnel effect in quantum mechanics, happening billions of times per second in the core of a star, in a self-sustaining reaction that began when the central temperature crossed 10 million Kelvin and has been running, in the sun's case, for 4.5 billion years. There is a beautiful diagram in astronomy called the Hertzsprung-Russell diagram, the HR diagram, that plots stars by their luminosity against their temperature or color. When you put stars on this diagram, they don't scatter randomly, they cluster in specific regions. The main sequence is the most prominent feature, a diagonal band running from hot, bright blue stars in the upper left to cool, dim red stars in the lower right, along which the vast majority of stars fall. A star on the main sequence is a star in the stable hydrogen-fusing phase of its life, and its position on the diagram is determined almost entirely by its mass. But below and to the right of the main sequence, in the cooler, less luminous region, there is another feature, the pre-main sequence tracks, when a young star is first revealed, when the T Tauri star emerges from its cocoon and becomes visible. It appears on the HR diagram not on the main sequence, but above it. It is too luminous for its temperature. This is because the star is still large, still puffed up from its formation, and a large star radiates more light than a smaller one at the same temperature. As the star contracts over millions of years, it traces a path across the HR diagram. In the 1960s, the Japanese astrophysicist Chushiro Hayashi worked out the theoretical path that a fully convective young star must follow during its contraction, a near-vertical track on the HR diagram that bears his name. On the Hayashi track, the star contracts at roughly constant temperature, its luminosity decreasing as its surface area decreases. Then, as the star becomes partially radiative in its interior, as the energy transport from the core shifts from convection to radiation, it transitions to a more horizontal track, contracting toward higher temperatures at roughly constant luminosity. This horizontal phase is called the Henye track, and eventually the star's interior temperature reaches the threshold for sustained hydrogen fusion. The contraction stops, and the star settles onto the main sequence. The journey from the cloud to the main sequence, for a star like the Sun, takes on the order of 10 to 50 million years. It sounds long. It is long, by human standards. But compared to the 10 billion year main sequence lifetime of the Sun, it is the blink of an eye. The Sun spent less than 1% of its total life getting to the main sequence. The rest has been, and will be, stable burning. Now, stars are not all alike. The scenario we've been describing, the collapse of a molecular cloud core, the formation of a protostar, the T Tauri phase, the ignition of hydrogen fusion, is the story for stars like the Sun. But stars come in an enormous range of masses, and mass changes everything. Stars more massive than the Sun burn hotter and brighter and faster, much faster. A star 10 times more massive than the Sun is not 10 times more luminous. It's thousands of times more luminous, because fusion rate scales steeply with temperature, and temperature scales with mass. More massive stars crush their cores harder, driving the core temperature higher, which means the fusion rate is much higher, which means the star is much brighter, and brighter means burning through the fuel faster. A star 10 times more massive than the Sun might have a main sequence lifetime of only tens of millions of years, compared to 10 billion years for the Sun. A star 40 times more massive might live only a few million years. These massive stars also form differently. Their formation is faster, more intense, and still less well understood than the formation of Sun-like stars. For one thing, massive stars don't form one at a time in well-separated cloud cores. They tend to form in dense clusters, where many stars are forming simultaneously, and their radiation and winds are interacting strongly with each other and with the surrounding gas. For another, massive stars reach the point of nuclear fusion while they are still accreting. They ignite their fusion while still embedded in their infalling envelope, before they have fully cleared their surroundings. This makes the formation of massive stars much more complicated to study. And at the other end of the mass spectrum, stars smaller than the Sun, low-mass stars, red dwarfs, are by far the most common type of star in the galaxy. They form more slowly, burn more gently, and can live for tens to hundreds of billions of years, far longer than the current age of the universe. A star with 1/10 the mass of the Sun will still be burning hydrogen when the universe is 100 billion years old, in a future so distant that the only stars left shining will be these dim red embers. The stars we see in the night sky, the ones bright enough to be visible with the naked eye, are mostly exceptional, unusually massive, unusually bright. The typical star in the galaxy is a dim red dwarf, too faint to see without a telescope, burning quietly and patiently in the dark. The places where all of these stars are forming, the active stellar nurseries of the galaxy, are among the most spectacular objects in the observable universe. And some of the most famous of them are visible to anyone who goes outside on a clear night and looks up. The most famous stellar nursery in the night sky, visible to the naked eye from anywhere on Earth, is the Orion Nebula, catalogued as Messier 42, M42, one of the jewels in the catalogue assembled by the French astronomer Charles Messier in the late 18th century. Messier was a comet hunter, and he compiled his list of fuzzy, comet-like objects not because he was interested in them, but because he kept mistaking them for comets and wanted a reference to remind himself to ignore them. He had no idea that his catalogue would become one of the most important reference documents in astronomy, providing names for the most spectacular objects in the northern sky. M42 is visible to the naked eye as a fuzzy patch of light just below the 3 stars of Orion's belt, in what corresponds to the middle star of the hunter's sword. To the naked eye, it looks like a star that isn't quite crisp, a soft smudge of light, slightly extended, slightly hazy. Through binoculars, it resolves into a cloud, a patch of luminous gas with structure. Through a small telescope, it becomes something unmistakably beautiful, a glowing cloud of pale blue and green and pink, lit from within, with 4 brilliant blue-white stars at its heart, arranged in a tight quadrilateral. Those 4 stars are called the trapezium, one of the most studied star clusters in the sky, and one of the youngest. The trapezium stars are extraordinarily young, only a few 100,000 years old, compared to the Sun's 4.5 billion years. They are also massive and hot, their surfaces burning at temperatures of 30,000 to 45,000 Kelvin, compared to the Sun's 5,700. And it is these four stars that light the Orion Nebula. Their intense ultraviolet radiation ionizes the surrounding gas, stripping electrons from hydrogen atoms and making the gas glow, a different color for different emissions, but predominantly a warm red-pink from hydrogen alpha emission, with green from doubly ionized oxygen and blue from scattered starlight. The Orion Nebula is, essentially, a bubble of ionized gas carved out of the surface of a much larger molecular cloud that lies behind it. That larger molecular cloud, the Orion Molecular Cloud Complex, extends across a significant portion of the constellation Orion and beyond, a vast structure containing roughly 100,000 solar masses of gas at temperatures near absolute zero, laced with magnetic fields, turbulent, and actively forming stars across its entire extent. The Orion Nebula that we see is just the lit-up face of this cloud, a relatively small region where the trapezium stars happen to sit near the surface, their radiation carving a cavity into the cloud face and illuminating it. Behind the glowing surface, deeper into the cloud, the star formation is ongoing. Hundreds of young stellar objects in various stages of their evolution, from the youngest, deeply embedded protostars detectable only in radio and infrared, to slightly older T Tauri stars surrounded by their disks, to stars like the trapezium that have already ignited and begun to blow away their surroundings. The Orion Nebula is about 1,400 light-years away, close enough that it has been studied in extraordinary detail by every generation of telescope, including, most famously, the Hubble Space Telescope. When Hubble turned its exquisitely sharp optics toward the Orion Nebula in 1994 and 1995, the images revealed something that had been suspected from ground-based observations but never seen with such clarity. Tiny dark disks surrounding many of the young stars in the nebula. Silhouetted against the bright background of the glowing gas, these disk-shaped objects, called proplids for protoplanetary disks, were unmistakable. Flattened structures of gas and dust, oriented at various angles to our line of sight, their edges dark against the luminous nebula behind them. Some had jets emerging from their centers. Some showed the characteristic shape of a disk seen edge-on, a dark lane bisecting an elongated bright structure. This was a remarkable moment. For all the theoretical work on disk formation and planet building, for all the indirect evidence that planetary systems should be common, here were the disks, visible, real, more than 100 of them identified in Hubble images of the Orion Nebula. Planetary systems in the making, 1,500 light-years away, photographed in enough detail to see their structure. The universe was making planetary systems not as some rare exception, but as a matter of routine. And yet, the trapezium stars present a challenge to these forming systems. Their intense ultraviolet radiation is photoevaporating the outer parts of the nearby disks, stripping away gas from the disk surfaces, gradually eroding the disks from the outside in. Disks too close to the trapezium are being destroyed faster than they can be replenished. This process, photoevaporation by nearby hot stars, may limit planet formation in dense star clusters, preferentially destroying the outer, icy parts of forming planetary systems and leaving only the inner rocky regions intact. The environment in which a planetary system forms matters enormously for what kind of system ends up surviving. Now, the Orion Nebula is not the only famous stellar nursery in the sky. Roughly 6,500 light-years away, in the constellation Serpens, lies the Eagle Nebula, Messier 16, and within it, one of the most iconic astronomical images ever taken, the Pillars of Creation. The pillars of creation are three towering columns of cold molecular gas and dust, rising from the surface of the Eagle Nebula's molecular cloud like enormous fingers. The image, captured by Hubble in 1995, is one of the most widely reproduced astronomical photographs in history. The columns are illuminated from above by the radiation of a cluster of young hot stars that have recently formed nearby, their surfaces eroded by that radiation, carved and sculpted into their dramatic shapes. The largest pillar is about 4 light-years tall. The width at the base is measured in light-years. These are structures of cold, dark molecular gas, as tall as the distance from our solar system to the nearest star, and they are being destroyed. The ultraviolet radiation from the young cluster is slowly photoevaporating the pillar surfaces, the same process we discussed in the Orion Nebula, but here made visible by the silhouetting of the dark columns against the bright nebula behind them. At the tips of the pillars, where the columns are narrowest and most eroded, are structures called EGGs, evaporating gaseous globules. These are dense knots of gas embedded in the pillar tips, being revealed as the surrounding less dense gas is stripped away. Some of them may contain protostars in the earliest stages of formation. The pillars may be triggering star formation even as they are being destroyed. The compression of the pillar surfaces by the stellar radiation driving new collapse even while the overall structure is eroded. The pillars themselves will be gone in perhaps 3 to 4 million years, a brief time by cosmic standards. And there is a strange twist in the story. The light we see from the Eagle Nebula took about 6,500 years to reach us. It left before the pyramids were built. Whatever is happening in the Eagle Nebula right now, we will not know for 6.5 millennia. The pillars we see may already be gone. There is something profound in that. The universe is so vast that even light, traveling at 300,000 kilometers per second, takes thousands of years, millions of years, billions of years to carry information from one part of it to another. When you look at the night sky, you are always looking at the past. The star you see is not where it is where it was, when the light that's reaching your eyes right now was emitted. Some of the stars you can see with the naked eye may no longer exist. Their light is still traveling toward you from stars that have since exploded. You are surrounded by light that carries news from the past, of events that may already be over. This is not a minor philosophical point. It is a fundamental feature of the universe we live in. And before we move on, there's one more class of object that deserves mention: the failed stars. Or, more generously, the objects that didn't quite make it. Brown dwarfs are objects that form by the same process as stars: collapse from a molecular cloud, development of a disk, accretion, but that end up with too little mass to sustain hydrogen fusion in their cores. The threshold is about 80 times the mass of Jupiter, or about 8% the mass of the Sun. Below this threshold, the core temperature never reaches 10 million Kelvin. Hydrogen fusion never ignites. The object glows briefly from the heat of its gravitational collapse, burns whatever deuterium it managed to accumulate, and then slowly cools and dims over billions of years, never reaching a stable equilibrium, never truly becoming a star. Brown dwarfs were predicted to exist decades before they were confirmed observationally. The first confirmed brown dwarf, Gliese 229b, was discovered in 1995, the same year as the first extrasolar planet around a sun-like star, the same year as the Hubble images of the Orion Nebula proplids. 1995 was a remarkable year for astronomy. Since then, thousands of brown dwarfs have been catalogued. They turn out to be common, perhaps nearly as numerous as true stars, though because they're dim, they're hard to find. They range in mass from just above the mass of large planets up to the hydrogen burning threshold, and they span temperatures from the thousands of Kelvin of the youngest and most massive, to room temperature, around 300 Kelvin, for the oldest and most evolved. Think about that. A brown dwarf, old enough to have cooled to room temperature. A star-like object, formed by the collapse of a molecular cloud, now sitting in interstellar space, barely warmer than the air in the room where you're trying to sleep. The universe contains objects stranger than any science fiction writer has yet imagined. The distribution of stellar masses, how many stars form at each mass, is described by something called the initial mass function, or IMF, first worked out by the astronomer Edwin Salpeter in 1955 using the then available census of stars. The initial mass function tells us that most stars form at low masses, that low-mass red dwarfs are far more common than Sun-like stars, which are far more common than massive blue giants. The relationship is steep. For every massive star with 10 times the Sun's mass, there are roughly 1,000 stars with 1/10 the Sun's mass. The galaxy is dominated, by number, by dim red dwarfs. The spectacular blue giants we see in stellar nurseries are rare exceptions, brilliant enough to be visible across thousands of light years, but numerically a tiny fraction of all the stars forming. Why does the initial mass function have the shape it does? Why do most cloud cores produce low-mass stars rather than high-mass ones? This is still an active research question. Part of the answer may lie in the gene's mass, the minimum mass for collapse, which, in the typical molecular cloud core, is a few tenths of a solar mass. Part of it may lie in how cores fragment. Large cores tend to break into smaller pieces before all the material can accumulate to one center. Part of it may lie in feedback, the radiation and winds from young stars disrupting the formation of further mass accumulation. The full story is still being assembled. Now, we've been talking mostly about stars forming alone, one star per collapsing core. But in reality, the majority of stars in the galaxy do not form alone. They form in pairs or small groups. Roughly half of all Sun-like stars are members of binary systems, two stars orbiting their common center of mass. The fraction is even higher among more massive stars. Most stars that have ever formed did so with at least one companion. Binary stars form from the same process we've been describing, but with a wrinkle: the collapsing cloud core fragments. Instead of all the material falling toward a single center, the core breaks into two or more pieces, each becoming a separate protostar. Fragmentation can happen during the initial collapse, if the core is rotating fast enough that centrifugal effects prevent all the material from reaching the center. It can happen in the disk, if the disk becomes gravitationally unstable and breaks into clumps. Or it can happen later, if two separately formed protostars in the same cloud core end up gravitationally bound. The resulting binary systems are extraordinarily diverse. Some binaries orbit each other in just a few hours, so close that the two stars are almost touching, their surfaces distorted by mutual tidal forces into egg shapes, mass flowing from one star to the other. Others orbit with periods of thousands of years, so wide apart that they barely interact, each pursuing an almost independent life while very slowly circling their distant companion. When massive stars form binary pairs and both eventually die as compact objects, neutron stars or black holes, the binary can survive multiple stellar deaths. As the two compact objects spiral closer together through the emission of gravitational waves, they eventually merge. Such collisions are among the most energetic events in the universe, producing kilonovae and synthesizing the heavy elements we discussed earlier. Stars also form in larger groups, clusters. Most stars appear to form in embedded clusters, groups of dozens to thousands of stars forming from the same molecular cloud within a relatively short time. These embedded clusters are initially invisible in optical light deeply buried in their natal cloud. But they glow brightly in the infrared, and eventually, as the most massive members ignite their fusion and pour out ultraviolet radiation, they blow away the molecular cloud and reveal the newborn cluster to the universe. Some clusters survive for billions of years. The Pleiades, visible to the naked eye in Taurus as a tight grouping of 6 or 7 stars, the Seven Sisters, is about 115 million years old. Its stars are still mostly hot and blue. The cluster still holds together. Other clusters disperse more quickly, their stars scattering into the general field of the galaxy within a few 100 million years. Our own sun almost certainly formed in a cluster, probably a moderately large one, but that cluster has long since dispersed. The sun's siblings, the stars that formed alongside it from the same molecular cloud, are now scattered across the galaxy. Astronomers are working to identify them by tracing stellar orbits and comparing chemical fingerprints. A few candidates have been identified. The sun had siblings. They are out there somewhere, burning quietly in the dark, unaware of their connection to us. All of this has been happening out there, in other molecular clouds, around other stars, in other times, but it happened here too, closer to home than any of the stellar nurseries we've just described. About 4.5 billion years ago, there was a molecular cloud, a giant molecular cloud, in what is now the outer Milky Way. This cloud was dark and cold and vast. Embedded within it, probably along one of its dense filaments, was a core, a concentration of gas and dust that had accumulated to the point of gravitational instability, and something triggered it. Something pushed that core over the gene's threshold and set it falling. We think we know what that something was, and the evidence comes from an unlikely source: meteorites. In the most primitive meteorites, the carbonaceous chondrites, ancient rocky remnants from the earliest solar system that have survived essentially unchanged since the planets formed, geochemists have found isotopic anomalies. The abundances of certain isotopes are not what you would expect from standard nucleosynthesis models. One of the most important of these is aluminum-26. Aluminum-26 is a radioactive isotope that decays into magnesium-26 with a half-life of about 700,000 years. It is produced in significant quantities by certain types of stellar nuclear processes, particularly in the final stages of massive star evolution and in supernovae. And it was present in the early solar system in amounts that tell us something important. It was produced very recently before the solar system formed. Recently, in this context, means within 1 million or 2 years, because aluminum-26 decays on that timescale, and if it had been produced much earlier, it would all have decayed before the solar system incorporated it. The inference is almost irresistible. A massive star, probably within a few tens of light years of the nascent solar system, exploded as a supernova sometime very close to the time that the solar system was forming. That supernova seeded the collapsing cloud with freshly made short-lived radioactive isotopes, including aluminum-26. And the shock wave from the supernova may itself have been the trigger, may have been the compression event that pushed a previously stable cloud core over the gene's threshold and set the solar system's story in motion. Think about what this means. The solar system was triggered into existence, possibly, by the death of a massive star, and that same death seeded the collapsing cloud with elements it had forged in its own core during its life: iron, calcium, silicon, oxygen, carbon, all the heavy elements, the atoms that became the Earth, the atoms that eventually became you, all of them seeded into the collapsing solar nebula by a star whose name we do not know, whose remnant we cannot find, that died more than 4.5 billion years ago. We would not be here without that death. The solar nebula collapsed. The clouds spun up and flattened. A protostar formed at the center, the nascent sun, embedded in its cocoon of gas and dust, shooting jets along its rotation axis, accreting furiously. The disk spread out around it, hot near the center and cold in the outer reaches. The chemical gradient along the disk determined what could form where. Rocky, refractory materials in the inner disk, where it was hot enough to keep only the highest melting point minerals solid. Ice and more volatile compounds in the outer disk, where temperatures were low enough for water and other ices to remain frozen. This compositional gradient is one reason the inner solar system has rocky planets and the outer solar system has ice giants and gas giants. Jupiter and Saturn caught enormous amounts of gas and ice from the outer, cold part of the disk, while Mercury and Venus and Earth and Mars built themselves out of rocky, metal-rich material from the hot inner disk. The Sun's T-Tauri phase lasted roughly 10 million years. During that time, its furious wind gradually cleared the disk of gas. By the time the T-Tauri phase was over, by the time the disk was mostly gone, the planetary system was already organized. Giant planets had formed, rocky planetesimals were colliding and building the inner planets. There was debris everywhere, and for hundreds of millions of years after the planetary system first took shape, that debris rained down on the young planets in an intense bombardment. The surface of the young Earth was hot, possibly covered in a global magma ocean from the energy of accretion. It was pummeled by incoming material. Its early atmosphere was probably blown away several times and rebuilt from outgassing and incoming comets. And somewhere in the midst of all that chaos, roughly 4.5 billion years ago, Earth found itself in its current orbit around a sun that had settled, finally, onto the main sequence. A star that had completed the long journey from cold molecular cloud to stable nuclear furnace. A star that would shine steadily for billions of years. A star around which, eventually, conditions would allow liquid water to pool, chemistry to complexify, life to arise. All of it because a cloud was cold enough and dense enough, and perhaps because a long-forgotten star died at just the right time in just the right place. Let's end with what stars actually make, because this is, in many ways, the most astonishing part of the whole story, and it brings us back to where we began, to the atoms in your body. The universe that emerged from the Big Bang, about 13.8 billion years ago, was almost entirely hydrogen and helium. About 75% hydrogen by mass, about 25% helium, plus trace, extraordinary trace amounts of lithium, the third element. That's it. 3 elements. Everything else in the periodic table was absent. All of the carbon and nitrogen and oxygen and silicon and sulfur and iron and every other element, all of it had to be made. And the only process in the universe capable of making it is what we've been talking about all night. Stars. Stars begin by fusing hydrogen into helium. This is the work of the main sequence, the long, stable era that our sun is currently in. Billions of years of converting hydrogen to helium in the core, slowly building up a helium ash at the center. When the hydrogen in the core runs out, and for the sun, that won't happen for another 5 billion years or so, the core contracts and heats up further, and eventually ignites helium fusion. Helium fuses into carbon and oxygen. The star's core fills with these heavier elements. For a star like the Sun, helium fusion is the end of the nuclear road. The Sun doesn't have enough mass, enough gravity, to compress its core to the temperatures needed for carbon fusion. When the helium runs out, the Sun will shed its outer layers in a spectacular but gentle expansion, becoming a red giant, then blowing off shells of gas in a planetary nebula, leaving behind the hot, dense remnant of the core, a white dwarf. That white dwarf will carry within it the products of the sun's nuclear burning, carbon and oxygen primarily, and will slowly cool over billions and billions of years, radiating its heat into space until it becomes a cold, dark object. The material blown off in the planetary nebula, the outer layers of the star, is returned to the interstellar medium, enriched with carbon and oxygen and other elements produced during the star's life. This is how stars contribute to the chemical enrichment of the galaxy, by processing hydrogen and helium into heavier elements and then shedding some of those elements back into space, where they become part of the raw material for future generations of stars and planets. But stars like the Sun make only carbon and oxygen in significant quantities. For the heavier elements, silicon, sulfur, iron, nickel, and especially elements heavier than iron, you need more massive stars, and what happens to them is far more dramatic. In a star several times more massive than the Sun, the fusion doesn't stop at helium. When the helium runs out and the core contracts further, the temperature gets high enough for carbon fusion. Carbon fuses into neon and magnesium and sodium. When the carbon runs out, neon fusion ignites, then oxygen fusion, then silicon fusion. Each successive burning stage produces heavier elements and releases less energy per reaction, so the star must burn its fuel faster to maintain pressure support. Hydrogen burning might last millions of years, helium burning hundreds of thousands, carbon burning thousands of years, neon burning perhaps a year, oxygen burning months, and silicon burning, the final stage, takes about a day. A day. At the end of that day, the silicon burning produces iron. And iron is where fusion stops releasing energy. Iron is the most tightly bound nucleus in nature. You can't extract energy from it by fusing it into something heavier or splitting it into something lighter. It is the bottom of the nuclear energy well. When silicon fusion ends and the core fills with iron, the star has lost its energy source. It has spent everything. Gravity, which has been held at bay by fusion for millions of years, finally wins. In less than a second, the iron core, roughly the mass of the Sun, compressed into a sphere about the size of Earth, collapses, falls inward at a quarter of the speed of light. The density at the center rises to nuclear density. The density of atomic nuclei, roughly 4 times 10 to the 14th grams per cubic centimeter, and the core suddenly becomes incompressible. It stiffens, and the outer layers of the star, which have been falling inward, bounce off the stiffened core and explode outward. A supernova, one of the most energetic events in the universe. In the moments of that collapse and explosion, in the fantastic temperatures and neutron fluxes of the imploding core and the shock wave expanding outward, elements heavier than iron are forged. Gold, silver, platinum, lead, uranium, all of the heavy elements that cannot be made by ordinary stellar fusion, because ordinary fusion can't push energy uphill past iron. These elements are made in the chaos of the supernova explosion, in neutron capture reactions that can add neutrons to existing nuclei faster than those nuclei can decay, building up to the heaviest naturally occurring elements. This process, called the R process for rapid neutron capture, requires the extraordinary conditions of a supernova or its close cousin, a neutron-star merger. When two neutron stars, the collapsed remnants of massive stars, spiral together and merge, they produce an explosion called a kilonova, and in those final moments they produce even more of these heavy elements. In 2017, gravitational wave detectors for the first time caught the signal of two neutron stars merging, and follow-up observations in visible light confirmed that the explosion produced enormous amounts of gold and other heavy elements. The gold in your rings, if you have any. The gold in fillings, in electronics, in jewelry around the world. A significant fraction of that gold was made when two neutron stars crashed together somewhere in the galaxy billions of years ago. Think about that the next time you see something gold. All of these elements, everything forged by generations of stars, from the first generation stars that formed from primordial hydrogen and helium, to the second and third and later generations, enriched by the deaths of their predecessors, have been cycled back into the interstellar medium, scattered into molecular clouds, incorporated into new stars, into planets, into you. You are the end product of this process. You are, in the most literal chemical sense possible, made of stardust. The calcium in your bones was forged in a star's helium shell flashes. The iron in your blood came from a supernova. The oxygen in every breath came from the oxygen-burning phase of a massive star. The carbon in your DNA was assembled in a red giant's core. The gold in any jewelry you own was forged in a neutron star merger. Every atom heavier than helium in your body has a stellar origin. The universe started with hydrogen and helium, and after 13 billion years of star formation, it produced you. You are what the universe has done with 13 billion years of stellar alchemy. So here we are, a process that started in the cold, dark interior of a molecular cloud, a region so quiet and so impossibly cold that molecules form in the dark and atoms slowly drift together, has given us everything you see when you look up at a clear night sky. Every star up there was born this way. Every single one of them collapsed from a cloud, built a protostar, developed a disk, blew jets, passed through its turbulent pre-main sequence youth, and finally, after millions of years of slow preparation, ignited fusion at its core and settled into the stable, self-sustaining fire it now maintains. Every one of them is doing what our sun does, converting hydrogen into helium, holding gravity at bay, one quantum tunneling event at a time. And there's something worth saying about scale. Not just the scale of stars and molecular clouds and the galaxy, but the scale of time. The universe is 13.8 billion years old. The Milky Way galaxy formed within the first billion years or so. The first stars formed even earlier, within the first few 100 million years, and they were different from the stars we see today. They contained only hydrogen and helium, the elements available from the Big Bang. They had no carbon, no oxygen, no iron. They burned hot and fast, and when they died, they seeded the interstellar medium with the first heavy elements. The second generation of stars formed from that enriched gas, and then the third, and so on, across billions of years, each generation building on the chemical legacy of the ones before. Our Sun is a relatively young star by galactic standards, formed only 4.5 billion years ago, when the galaxy was already 9 billion years old. It inherited 2% of its mass in heavy elements from all the previous generations of stars that lived and died before it. That 2% is what made the Earth possible, what made us possible. We are, in a sense, the beneficiaries of billions of years of stellar chemistry, of all the stars that lived and died before the Sun was born, each one contributing a little more to the growing inventory of elements that eventually, in our molecular cloud, reached the critical concentration needed to build a rocky planet with oceans and an atmosphere. Think about what it means that you are here at this particular moment in the universe's history. Early in the universe, in the first few billion years, there were fewer heavy elements, fewer rocky planets, fewer of the chemical building blocks that life seems to need. The universe, in some sense, had to grow up before it could produce the conditions for biology. And we are here at a time when the galaxy has been enriching itself with heavy elements for nearly 10 billion years. A time when there are trillions of planetary systems in just our galaxy alone. A time when the conditions are, cosmically speaking, rather good for life. You are not an accident of a random universe. You are the product of a universe that has been patiently building its way toward complexity for nearly 14 billion years. And there is another way to think about the scale of what we've been describing tonight. The nearest stellar nursery to Earth, the molecular cloud complex in Taurus where T Tauri itself lives, where hundreds of young stars are forming right now, is only about 450 light-years away. In cosmological terms, that is right next door. The photons leaving those young protostars tonight will arrive at Earth in 450 years, long after everyone alive today is gone, but in a time that human civilization can still plausibly imagine. 450 years ago, Galileo had not yet built his first telescope. The Americas had only recently been contacted by Europe, and the light now leaving the Taurus star-forming region will arrive in an era as different from ours as ours is from that one. The Orion Nebula, at 1400 light-years, is more distant, but still close. The Carina Nebula, where Webb photographed the cosmic cliffs, is 7,500 light-years away. The Eagle Nebula, home to the pillars of creation, is 6,500. All of these are within a small portion of the Milky Way, which is 100,000 light-years across. The universe is 280 billion light-years in diameter, the observable portion of it. We are looking at star formation in our backyard. And yet even this backyard is enough to fill a lifetime, many lifetimes of study. There are hundreds of known molecular clouds within a few thousand light-years of Earth, each containing hundreds to thousands of young stellar objects in various stages of formation. There are thousands of known T Tauri stars, hundreds of confirmed protoplanetary disks, dozens of known binary protostellar systems. The sheer volume of data, of observations, of questions waiting to be answered is more than any single scientist could work through in a career. This is the reality of modern astronomy. The universe is not running short of things to show us. Every new telescope, every improved detector, every new technique of analysis opens new windows and reveals new phenomena. The story of how stars are born is not finished. It will not be finished in our lifetimes. It is one of the great ongoing investigations of science, perpetually surprising, perpetually deepening, perpetually more wonderful the closer you look. And star formation isn't finished. It isn't something that happened a long time ago. Right now, in the Orion Molecular Cloud Complex, 1,400 light-years away, protostars are forming tonight. T Tauri stars are furiously clearing their surrounding disks. Jets are punching through molecular gas. Somewhere in the galaxy, a molecular cloud core has crossed the gene's threshold within the last few thousand years, and it is beginning to fall inward, and in perhaps 100,000 years, if all goes well, a new star will ignite that isn't shining tonight. The universe is still building itself. The process that made the sun and seeded the solar system and built this planet, that process is ongoing, all around us, everywhere, at this very moment. And it's happening inside you. Right now, the calcium in your bones, forged in a stellar core, is doing what calcium always does, holding your skeleton rigid, enabling your muscles to contract. The iron in your blood is carrying oxygen from your lungs to your cells, doing its ancient work, the same work it was built to do in the nuclear furnace of a star that died before the Earth existed. The carbon in your DNA is carrying the instructions that make you you, woven into a molecule of extraordinary complexity, by the same chemistry that fills the dark interior of molecular clouds with organic compounds. It's all happening effortlessly, the way it's been happening since long before anyone was around to wonder about it. The universe figured out how to make stars long before we did. Stars figured out how to make elements long before we figured out they were making them. And now you know a little more about how both of those things work, about the cold, dark clouds, and the slow collapse, and the spinning disk, and the furious youth, and the quiet ignition, and the billions of years of stable burning, and the spectacular death, and the scattering of elements into space, and the gathering of those elements into new clouds, and the new stars, and eventually, after an almost unthinkable length of time, this, a planet, an ocean, a living thing, a mind thinking about how it came to be. That's a good thing to carry into sleep, the knowledge that the world is stranger and more wonderful than it appears, and that understanding it, even a little, is one of the finest things a human mind can do. So let that settle, let the ideas drift, and let the quantum mechanical processes in your neurons, in those carbon-based, iron-tinged, oxygen-breathing, star-forged atoms, carry you gently, reliably into sleep.